Okay, so if we want to combine IPv6 with the IEEE standard 802.15.4, we have to make some adjustments because IPv6 is a next generation protocol. We have a large number of addresses. We have the automatic address generation. We have security, and it's an open standard. But the main problem with IPv6 is a large header. We have a header of 40 bytes, and if we want to employ this on such low power networks like IEEE 802.15.4, we have to make some header compressions. So for this, the 6LoWPAN standard was developed. So it's an open standard. Hello. This open standard describes how we can transmit, and the main advantage of 6LoWPAN is that it works completely transparent. So this I will show at a network stack. So here you can see a comparison between 6LoWPAN with an attached network and a proprietary solution. So in the proprietary solution you have your application, and underwards you have some kind of network stack like Zigbee, and the packets are transferred over the WPAN standard. So a big problem in this scenario are the gateways. So inside the gateway you have to go back to your packet or your payload, and then you have to do some kind of address mapping, and then you can put this in a normal IP stack. In our solution, and transported with IPv6, and after a header compression of 6LoWPAN, the packet is transported over the LoWPAN. And in this scenario, the gateways are quite easy. So we take our packet, and after processing the 6LoWPAN header, we have a normal IPv6 packet, and this packet we can just put in a normal local area network like Ethernet. And it's quite easy to set up a server or a normal PC to receive the packets. So here I have a short overview or short comparison against other solutions to transfer wireless packets. So if you compare, you see that the range of a SubGHz 6LoWPAN implementation is quite good compared to Bluetooth or Wi-Fi. Also, the WPAN standard is designed for low power consumption. And with 6LoWPAN we have Internet protocol, but the only disadvantage is a really low data rate. So all these protocols are developed for low data rates network like sensor networks or networks with controlling application. We also support meshing and multi-hop, so that means if you have to bridge over a really long distance, you just add some hops in the middle, and so we can communicate from the gateway to the end node with hopping. And one main advantage of a SubGHz solution is that you can use a less crowded frequency band. So all in all, we can say it is suitable for low power and low data rate IPv6 network applications. Okay, let's continue with our module, with the hardware. So our module supports the European frequencies and the North American frequencies. In Europe, we support 4 channels, and the data rate is 20 kilobits per second in the BPSK mode, or 100 kilobits per second in the QPSK mode. The output power is 5 dBm, and the sensitivity is -110. In North America, we have 10 channels, and also in North America it's allowed to use higher output power. And then the sensitivity in North America is comparable to the European sensitivity. One advantage of the IEEE 802.15.4 standard is that the DSSS, the spread spectrum technology, is mandatory for all implementations. So here you can see a picture of our module. Our module consists of a transceiver and a microcontroller. We are using a 32-bit ARM Cortex-M3 Cortex-M3 microcontroller with 256 KB flash and 48 KB RAM. And this microcontroller can run up to 64 MHz. The power consumption of the whole module in the transferring mode at 0 dBm is 18.5 milliamps, and during the receiving mode it's 13.5 milliamps. In the standby mode, we can go down to 3.5 microamps. The supply voltage can vary from 2 up to 3.6 volts. So it's quite easy to add maybe a battery or a simple power supply to our module. The microcontroller gives up a large possibility of interfaces and peripherals. So we have up to 19 GPIOs, 2 UARTs, SPI, USB, I2C, and a CAN bus interface. We have also 8 ADCs and DACs, 11 PWM outputs. We have timers, CRC generators, and we have 2 watchdogs. Currently, we have 2 different modules. One module has edge board contacts and 13 pins, and to connect an antenna we have an UFL connector. The new module is an LGA package, so you can solder this module directly on a PCB. We have 2 additional pins for an external RTC crystal oscillator, and this module is a little bit smaller and also cheaper. To connect our wireless solution to existing networks, we provide an Ethernet gateway, also a USB network stick, and for the development we have some kind of snap-in adapter where you can put just the module inside this adapter to program it. If you want to start to develop some application, we recommend our development kit. So this development kit, a module is soldered on a development board. This board allows you to communicate with the module via a virtual COM port, and also a JTAG adapter is integrated. So if you want to start, you just attach this development kit to your PC, start your IDE, and then you can start to develop your first application. Also, we have an SMA antenna connector, and the antennas are inside the development kit. So this development kit, as you see, consists of 3 development boards, 3 antennas, battery packs, USB cable, and all the software and documentation packets. So with this development board, it is possible to create your first application within 1 hour. Let's continue with the software. So all the software for the module are royalty free, so you get an CIPI library. With this, you are able to develop your own application. So here you can see the structure of our software. So we have some libraries supporting the interfaces like the UART or the SPI. We also have libraries with IPsec and the key exchange module, and we also have the 6LoWPAN library that bridges or that allows to communicate via UDP. Another feature is the over-the-air update. So our modules are able to do an over-the-air update. So with our C library, you develop your own C code and link this code against our library. And both the C library, the network stack, and your application are running at our module. So you don't need an external microcontroller. And it also has a small event-based operating system. As I described before, the 6LoWPAN IPv6 network stack is included, as well the IPsec and IKV2. Also, it is possible to use several peripheral libraries. You can use the ST library and some small libraries from our company. You have full access to the whole MCU. You can set up the ADC by yourself. You can do whatever you want. But all our software is optimized for the ease of use. Furthermore, if you decide that you have your own microcontroller and you want to interface with our modules, we provide a serial command interface. It's connected via UART or SPI. It allows a remote configuration, and we provide some kind of AT commands like commands to control and to send packets. Furthermore, we offered some code for Ethernet gateways, UART gateways, or USB gateways, and all this code is given for free. And furthermore, you have some kind of a sniffer functionality. So we have a software that runs on a PC, and you can see the whole traffic inside your wireless networks. So at this point, I will show you how easy it is to create some applications. So I would like to show you some kind of temperature sensor example. In this example, each temperature sensor in each module should report the temperature every half of a minute to a host computer. And in this scenario, we would like to use the Ethernet gateway. So on the left side, you can see the server or normal computer with the given IPv6 address. So and here you can see the code. So after booting up the network node, the function in line number 5, SWIR up init network, is called. Inside this function, we will read the temperature sensor and get a temperature value. In line number 8, you can see how easy the temperature value is transmitted to the computer. So we just call the send UDP2 with the pointer of the temperature value and the size, and also the remote address of the computer and the port number. Afterwards, the stack will send the UDP packet to the computer, and then line number 9, we are calling our power down function, and after executing this function, the stack will wait till the packet is sent to the computer, and then it will send the module into the standby mode for the next 30 seconds. So as I described before, we have 3 different gateways. They are all working completely transparent. So if you attach a gateway to your given network, you can ping the modules, you can communicate with the modules without thinking about address translation or something else. So the Ethernet gateway is completely independent from the operating system, and it can be just added to a normal switch or a router. Furthermore, we have a USB gateway. For this USB gateway, we have drivers for Windows and Linux. We are using for this the default drivers. And of course, we have a TAN-TAP gateway. this creates a virtual network interface on a Linux PC, and in this scenario, the module or the gateway is attached or communicates via a serial interface with the PC. And as I said before, the source code is running on the development board, and all the source codes are given for free. So we have a sniffer to observe the network traffic, and the sniffer comes with a graphical front end for Windows and Linux. We have an over-the-air update front end where you easily can broadcast a new firmware to the existing modules in your networks, and we recommend Rowley's Cross Studio for the development, and for this we have some support packages, so you just easily install the support packages, and afterwards you can create a new project for our modules. To the security. So if you have wireless networks, everybody can listen to your traffic, and everybody can create traffic and manipulate the traffic. So we have several security requirements. We have to ensure the data confidentiality, the data integrity. We have to authenticate the sender, and we have to protect our network against replay attacks. The best security solution to communicate over untrusted nodes is an end-to-end security. This allows us to communicate over the internet or other unsecure networks, and only the endpoints are able to secure and unsecure the packages. IPv6 requires IPsec as a security standard. This standard is open, so everybody can prove the standard, and it supports, or this gives us a solution to protect our packets against all kinds of attacks. But IPsec is only a standard to protect our packets. So an additional problem is the key exchange. For this, we have the Internet Key Exchange Protocol in the second version. This is also a standard, and it's recommended for IPv6 devices. This standard allows us an automatic key exchange with a Diffie-Hellman key exchange between two nodes and the authentication. So all in all, IPsec and IKV2 are the best solution for these networks to give a higher security, and both standards are widely used today in VPNs and virtual private networks. So on the right side you can see the network stack, and you can see where IPsec is employed in the network stack. So it works completely transparent for the application and for the UDP. As I said before, it's an open standard. You can see it in the RFCs, and IPsec provides an extra payload, the encapsulated security payload, where all the UDP and application payload is encapsulated. And on the other side, we have the key exchange protocol. This protocol is needed to create keys for the IPsec. IPsec is working in IPsec is using symmetric cryptography, and to exchange the key, we have to use asymmetric cryptography. This needs a lot of computational power, but it's also possible to run this on a small microcontroller. we are able to do a key exchange into 4 seconds on each side on the module. Okay. On the next slide, I will show you some application or fields where we are using our modules. So in the first, we have the M2M communication, or we have just the cable replacement. We also use our modules in the solar monitoring, home automation, street light control. Also, with our security systems, we enable some customers to create locking systems or keyless entry systems. And of course, it is possible to create some metering application. So at the end of my short presentation, I will summarize all the information. So the main application are industry and home automation. We support smart grids and smart metering. We also provide keyless, or we are helping to provide keyless entry systems. Our module or our software stack provides an IPsec and IKV2 library. We have a 32-bit microcontroller, so there's no need for an external MCU, and we have a lot of interfaces. Our IPv6 6LoWPAN implementation is supports a mesh protocol and network with network layer security. Our module is optimized for low power consumption, and it also comes with a small footprint. We provide a C API and a serial command interface. So the main benefits are that we only use standardized protocols. The software stack is completely royalty-free, and it's a plug-and-play communication solution. And I show you how easy it is to implement some application to transmit some data. So it's quite easy to develop ready products in a really short time. Okay, thank you for your attention, and if you have some question, please feel free to ask.
All right, thank you, Mr. Fröhlich. We will end this presentation that I put everybody now on unmute everyone. So if everybody or if anyone has a question, you can ask it in a few seconds as soon as I have every line open. Just a second. So now every line is open. Does anyone have a question for Mr. Fröhlich?
Yes, I have a question. You hear me?
Yeah.
Okay. Pascal Champanet from Adonis Radio Frequency. In the example of the temperature sensor, which means there is only few bytes to transmit, I would like to have an idea about the size of the transmitted packet and also the transmission latency regarding the lowest data rate of the module. Thanks a lot.
Okay, so IPv6, or for IPv6, it is mandatory to have an MTU of 1,250 bytes. So in our implementation, it is possible to send large packages up to 1,250 bytes. and the 6LoWPAN will fragment this payload to to some more packages, and at the end all the packages will be reassembled. So at the slowest data rate, if you have only a couple of bytes to transmit, we need around 40 to 50 milliseconds for one transmission. And it's quite easy to verify this. If you have the module, you can just do a ping at the console, and then you can see the round trip time. And if you hit half the time, then you have the transmission time.
Thank you. Does it mean that you transmit the whole IPv6 packet, or you reduce it regarding the small size of the real payload?
Now, the 6LoWPAN firstly compresses the header, so we have really long addresses, and it is possible to compress the addresses and other parts of the header. So this reduces the header up to 10 bytes or 5 bytes. It depends on the addresses. And then we fragment the whole packages. So if we want to transmit, for example, 200 bytes, and we are able to put only 80 bytes in one packet, we have to transmit 3 or 4 packages to transmit the whole IPv6 packet. But this is completely transparent.
Yes, but it means you always transmit the complete IPv6 packet with a compressed header.
Yes, exactly.
Yeah, okay. Thank you very much.
All right, do we have any other questions?
Yes, I've got a question. Nicolas Renaud from Bouygues Telecom. Do you hear me?
Yes.
Yeah. So I wanted to know if there is a way to implement into your solution a co-op library.
Pardon? Again, sorry, it was bad to understand.
I wanted to know if this is possible to implement into your solution a co-op library. This is a REST, asymmetric REST solution to communicate with the object of Internet.
Yes, this is possible. So a couple of years ago, we did some experiments with co-op. So if a customer wants to implement a co-op, we can support them to do this. So it isn't a problem. So for example, you can take the co-op code from Contiki, for example, and port this code to our network stack, and this is quite easy. So this is done in maybe in an hour.
Okay, and is it your solution is not Contiki based?
Yes, our stack internally is a Contiki stack, but we only use the micro IP stack from Contiki. But we did some modification regarding to the performance and stability. So there are still some issues inside the Contiki stack, and in our solution we try to solve this issue.
Okay, thank you.
Okay. Is there another question, maybe? If not, maybe also for your information, if you'd like to have the presentation we saw today, please write an email to me, and then I can forward you the information and the presentation. Also, if you have any other question after the presentation, please just write me an email again, and I will also can set up the contact to Mr. Fröhlich or to ZMDI in general. All right, so if there is no more questions, or if there are no more questions at the moment, I would like to thank you everyone for your attention, and I wish you a nice afternoon.
Thank you very much.
Thank you, bye-bye.
Bye. Bye-bye.
Thank you.
Bye.
Thank you.
Gut, vielen Dank, Herr Fröhlich.
Gerne, gerne.
Tut mir leid, dass anfangs wohl noch der ein oder andere ist dazugekommen.
Ja, ist ja kein Problem. Damit müssen die Leute halt leben, dass ich halt den Satz nochmal angefangen habe.
Genau. Genau. Und dann, wie gesagt, wäre gut, wenn Sie mir einfach das PDF zuschicken könnten, wenn dann Anfragen kommen, dass ich eventuell, also was Sie eben dann, was wir daraus verschicken können.
Genau.
Genau, das wäre super. Und wenn sonstige Fragen sind, dann werde ich die Leute natürlich auch, wenn es okay ist, dann an Sie weiterleiten oder den Kontakt zu Ihnen herstellen.
Gerne, gerne. Also Telefonnummer, E-Mail-Adresse ist kein Problem. Also Sie können gerne anrufen.
Mhm. Super. Genau, dann werde ich jetzt selber mal gucken. Hier die Nachverfolgung machen, dem Herrn da vorstellen, auch noch die Liste zukommen lassen.
Könnte ich damit auf CC kommen, dass ich auch einfach mal einen Überblick habe, wer